Okay, so thank you very much for giving me the opportunity to speak here about the project that I was working on together with Pavol Ševera. I should first say that it is related to the mini course that Pavol was giving last week, but I will make it nevertheless self-contained so that you don't need to have followed the course. So it should be self-sufficient. Yeah, so it is based mainly on this article and to a lesser extent on the older one. So what I would like to talk about is equivariant Poisson-Lie T-duality and supergravity. And yeah, so I will explain what these terms mean in a moment. So let me start with the standard beginning, and that's Courant algebroids. So Courant algebroids. So that's the first part. So I guess many of you know what this is, and in case not, then let me write the definition. So a Courant algebroid is the following structure. So there is a vector bundle. E over M. So we will keep this notation throughout the talk. There is with some extra structure. So there is three operations. There is first of all there is a pairing. So this is a one can say fiber-wise inner product. So fiber-wise inner product. Then there is the so-called anchor map. So this is a vector bundle map from E to the tangent bundle of the base. And most importantly, there is a bracket. There is a bracket on the space of sections. So it takes two sections and produces another one. And it is R linear. And such that there are some axioms. Okay, so the axioms. So first of all, the bracket itself, the bracket preserves itself, or it acts as a derivation of itself. So this is the. So if the bracket would be skew-symmetric, antisymmetric, then this would be the Jacobi identity. But the bracket is in general not antisymmetric. But instead it has a. So if I take, for example, A, B, so the symmetric part of it is given by taking the inner product, then taking the differential of it. So this is a one form. It's a section of T star. So I can apply the transpose of the anchor map. So the anchor map goes from E to Tm. So the transpose goes from the dual to the dual. But okay, so rho transpose, it goes from T star M to E dual, but I can identify this using the inner product with E. So this is one of the axioms, and then there is two more, or one or two more, depending on the wait. Okay. So this axiom tells us that the bracket preserves the inner product. B, A, C. And finally, yeah, and one can also put the compatibility with the anchor map. So in all that I have written, these A, B, C, they were sections of E. And now f is a function on the base. So f is a function on the base. Then this axiom tells us that this is not C infinity linear in this slot, but instead there is the action of the anchor. Okay, so that's a lot of axioms if you haven't seen it before. So it's better to illustrate it on some examples. So example. If we take M to be a point, then E is just a vector space, right? Because it's a vector bundle over a point. And then this bracket will just correspond to a Lie bracket. So there is, in fact, so this is a Lie algebra G, and we have to supply also the inner product. So each time we have a Lie algebra with an invariant pairing, then this gives a Lie Courant algebroid in this way. So the anchor map is trivial, and the Lie bracket is, and the bracket is just the Lie bracket on G. Yes, so.
So since the bracket is not antisymmetric, shouldn't one also write a rule for what happens when the function is on the first slot?
It follows from this one and this one.
Mm-hmm.
And you want me to write it?
No, it's okay. But it just doesn't look that nice, right?
Yeah, if I would have a function in the first slot, then it goes out, it looks different. There is an extra term here, and this is the consequence of this one. Yeah, thank you. That's good to say. Okay, yeah, so the second example, where the base is not a point, but it's a general manifold, is the following one. So take, as a vector bundle, take this direct sum of t and t star. And, okay, now, okay, so the anchor here will be just the obvious, the projection to the Tm part. The pairing will be just the usual pairing of brackets, of vectors and covectors, but the bracket is more interesting. So if I want to take a section, then section of E is a sum of a vector field and one form. So let's take U and alpha, and V and beta, and the bracket here is given by just the usual Lie bracket of vector fields plus Lie derivative with respect to U of the one form beta. Okay, let me continue here. There is minus contraction with V of the alpha. And in general, one can also add another term where H is some closed tree form. And you can check that this structure satisfies the axioms above. And in some sense, you should think that of these two as the main examples of that structure. So Lie algebras and and algebras of this form. Yes, okay, very good. And now there is a theorem. Oh, okay, let me maybe say it like this. So you can show, so the remark, that for an arbitrary Courant algebroid, just from the axioms, you can show that if you construct this, so here you use the anchor, and here you have the transpose of the anchor. So you can show that from the axioms it follows that this is a complex. So if you take row transpose and apply row again, then this gives you 0. And in the special case when this is actually an exact sequence, then you call Courant algebroid exact. So if this is exact, then we call Courant algebroid exact. And to finish this part, there is okay, I need another board. So there is an important theorem by Pavol Ševera saying that every exact Courant algebroid is of that form, is of the form, we call it example of this form, T plus T star. And moreover, two such exact Courant algebroids are isomorphic if and only if they differ, but if and only if the corresponding three forms are cohomologous. Isomorphic if and only if H and H prime differ by some dB. So as a consequence, the exact Courant algebroids over a given manifold M are classified by the third cohomology class. Yes, very good. So these are Courant algebroids. You should really think of those two examples as being the main protagonists of this structure. But then now we want to say something about structures that we can build on Courant algebroids. So for the purpose of making connections with physics, with supergravity, or some string sigma models, we need to introduce what is called generalized metric. So let me talk about structures. Structures on Courant algebroids. So first of all, the most important one is the so-called generalized metric. So a generalized metric So yeah, I know that there is an overlap with what Pavol was telling us last week, so I am sorry for those who watched it and now have to watch this again, but I will soon get to some different things than from what Pavol was telling us. Okay, so generalized metric is a subbundle. There are some equivalent formulations, but for us the best one is to say that this is a subbundle of the Courant algebroid, which satisfies the property that if we restrict the inner product on V+, then it is positive definite, and on the complement, so the pairing on the complement of V+ is negative definite. Okay, and just for short notation, I will call this V+ perp, I will call it V-. So that's the complement. So to see why this is interesting, so there is an easy proposition that if you fix a manifold M, okay, so let M be a manifold, then there is a one-to-one correspondence between exact Courant algebroids over M with a choice of a generalized metric. There is a one-to-one correspondence between this one and with the data of a metric, or Riemannian metric, and closed tree form on M. Okay, so this is a closed tree form, and this one is a Riemannian metric. Okay, so I won't go into the proof of this, but basically the idea is that if you have an exact Courant algebroid, then you can see it as T plus T star, and therefore the V+ with these properties will be, so if you have T and T star, then V+ will look somehow like this. So you can see this as a graph of some two tensor, and there is a unique. And you can choose a different, well, this identification is not canonical, you can choose it somehow differently, and at the end, these three forms will differ by some exact piece, and there is a unique identification for which this V+ is a graph of a metric. So this is how we get a metric, and H is then the corresponding tree form. But anyway, for us what is important is only this one-to-one correspondence here. Very good. And the second piece of data that we have is a so-called divergence map. So divergence is a map that goes, let me call it div, which goes from sections of the Courant algebroid to functions on the base. And we have one condition on that. We want that the divergence, if we take a section and multiply it by a function, then we want this to be not just this one, but there should be this condition. So this indeed corresponds to the usual divergence that people usually use. For example, so this is one example. So if you have a volume form, or a density. So suppose mu is a density or a volume form. then for such piece of data, we can define a divergence, which is given simply by taking a Lie derivative. So we make a vector field out of the section. We have some vector field, and then we act on the density. We get another density, so we take the ratio of those. So in this sense, this is the usual notion that you have a density or a volume form, and your divergence tells you how does this change under the vector field. How does the volume change? Okay, so these are the two important structures that we have on the Courant algebroid. We will see in a moment that when we want to make a connection with physics, then this generalized metric will be the gadget that encodes the metric and the B field or H field, and divergence will correspond to the dilaton. But before that, I want to say a few words about Poisson-Lie T-duality. So, okay. So I will start with the following definition. So suppose we have two Courant algebroids, E over M and E prime over M prime. So these are two Courant algebroids. And suppose we have a map F that goes from M prime to M, and that this is a surjective submersion. Surjective submersion. Now we say that E prime is a Courant algebroid pullback of E. If, first of all, okay, what's the best way to say this? So if it is if E prime is as a vector bundle, this is a pullback of E. Okay, so that one is easy, and we want the structures to be compatible. So if you think about it, we want the three structures, the bracket, the pairing, and the anchor be compatible. So the only way you can cook up is that, for example, if you take two sections, U and V, and you do the bracket, then this should be the same as if you would do the bracket and then pull back. Same thing for the pairing. And finally for the anchor, so if you take a section U on E, okay, so probably I should draw a picture. So if you take a section here, and you pull it back, and then apply the anchor, you get a vector field here, and then when you push it forward, so you want that this is a well-defined, and this recovers the anchor on the right-hand side. Maybe I can put to the structures here, I can maybe put a prime. So let me put prime here, and prime here. Yes. Okay. And very good. So an example of that, and this is the one that should be familiar to those who know Poisson-Lie T-duality. So suppose that you have a Lie algebra with invariant pairing. People call it quadratic Lie algebra. Pairing. And suppose furthermore that there is a subalgebra of this one, which is Lagrangian. Okay, so this means that the induced pairing vanishes and it is half-dimensional. Okay, so if you have such a data, then you can form two Courant algebroids. First Courant algebroid is just, well, this G itself, right? So G seen as a Courant algebroid over a point, right? That was our example number one. And there is another Courant algebroid you can craft out of this data, and that one is you take the quotient G mod H, and you take basically you take, okay, now I'm drawing in the let me keep it aligned like this. Yes, to make a connection with that. So you consider a map to the point and you pull back this vector bundle. So you just get a trivial bundle, G mod H. And the claim is that there is a unique Courant algebroid structure on this guy, which makes it into a Courant algebroid pullback, such that you want that the anchor here, so the anchor on the left should be just the action, is the action of G on G mod H. Right, so this is a quotient from the right. So you still have the group G acting from the left on itself, and the corresponding infinitesimal action will be given by a map from G mod H here to here. So, and that's exactly what you want to have for an anchor. So the claim is that there is a unique Courant algebroid structure satisfying this property. Yes, thank you. Thank you. Yes, very good. So now the cool thing about this guy is that because of the Lagrangianity here, you can check. This is actually a very simple check, just counting some dimensions. You will see that this is not just any Courant algebroid, but it is exact. Okay, so that's an important thing. So this guy on the left, not this one, but this one is exact. And just from counting dimensions and knowing that it is exact, we can use theorem by Pavol, and we know that this is necessarily of the form T plus T star. And that is cool because of the following reason. So let me just make one final definition. Yes.
Sorry.
Definition.
Fridrich, T plus T star of what?
Of the base, G mod H. Oh. So since this is exact, then yeah. Okay. Okay, so we say that two exact Courant algebroids are Poisson-Lie T-dual. If they are both pullbacks of one Courant algebroid. If they are both pullbacks of some other guy, of some E over M, some Courant algebroid. This one doesn't have to be exact. Yeah, but so if you have two Courant algebroids and they happen to be in this relationship that they are both pullbacks of one common ancestor, then you call them that. Then you say that they are Poisson-Lie T-dual. So, and the reason for that is very simple. So going back to that picture. So suppose now that we have. Okay, or maybe we can be even more general. So let us look here. So suppose that we have a Courant algebroid, E over M, and we have two different Courant algebroid pullbacks. So there is M prime here, and there is M double prime, and there is some Courant algebroid here, and there is some Courant algebroid there. And we want that this and this guy are exact. Okay, so that's just to remember. So if we have such a setup, so then we say that this and that Courant algebroid are Poisson-Lie T-dual. And so the reason for that is that whenever now we pick a generalized metric in this guy in the middle, so we pick some V plus. Can you see that this is a different color? Okay. So each time we have a generalized metric here, which is just some subbundle, then we have an induced generalized metric here. Sorry? Okay. Okay, it's probably not that important, but no. Maybe green. Also not, right? Okay. Anyway, okay, let me keep this one. So since the fibers of this thing are just the fibers of here, then and this is a subbundle, then we can just naturally get the subbundle here and over there. But now we remember the proposition from here that we have an exact Courant algebra with a generalized metric. So this is the same as having on this manifold M prime, having some metric and some free form. And in the same way, we get such data on the right. Right? Because we have an exact Courant algebroid and the generalized metric. And now, whenever we have a manifold and a metric and a closed tree form, we can construct a sigma model. And correspondingly a sigma model here. Okay, I will be more explicit in a second. But the claim of Poisson-Lie T-duality is that these sigma models, or the dynamics of these sigma models is isomorphic, or almost isomorphic. So it is really some sort of duality. Yeah, and so what do I mean by sigma model? I mean that whenever we have such a data, then you can consider maps that go from some, let's say, Riemann surface to M prime. And then we can build an action function now, which will be just given like this. Okay, I should put primes everywhere, because there are primes here. And here, there should be some Vezumino term. So this Y is a manifold satisfying this property. I should put primes everywhere. Sorry, say again? Oh, yes, thank you. Yes, right. Yeah, and here, there should be sigma. Yeah, sigma doesn't have a prime, okay. Yes. Right, yeah, so the claim is that these two models are dual. Okay, but let me now go to the, yes? Yes, they have to match because, so in the, oh yes, so the question was if the dimensions of M and M prime have to match. Sorry? Wait, so, oh yeah, sorry. Right, so in general, so these two dimensions have to be the same. So the reason for that is that, so for the fibers, so the fibers here are the same as fibers here. So if this has some rank, then this has the same rank. But since it's exact, it has to be, the rank is twice the dimension of the base. So that's why the dimension of this guy is half rank of this thing. And this thing should be smaller because there is a surjective submersion. So yeah, maybe let me draw the example for this one. So the easiest way to have such a pair is to have the same thing as here. So we have some Lie algebra with some pairing, and we have an H, a Lagrangian subalgebra, and we have another H. Okay, so they are both Lagrangian, and then we just have this picture. There is G mod H. There is G mod H prime, yes. And lift. Thank you. Yes. Yeah, so this is the easiest setup. And so whenever now I have a generalized metric here, then this will give me generalized metric here and here. Okay, now I am. Okay, to make a correspondence with that, I should probably call. Let me call this H prime, and this is H double prime. Okay, so that I will have the correct number of primes. Very good. Yes, and so we get so eventually what we have is we get a sigma model on this target, on G mod H prime. And here we get a sigma model on G mod H double prime. And now,
well, I wanted to ask a question. I didn't want to interrupt you. So if there is anything that you want to add, just go ahead and I'll ask my question.
oh, okay. No, you can ask.
Okay, so I'll ask a vague question with a firm field theoretic intuition, but I'm not sure the answer, there exists an answer in the simple T-duality world. Is there anything such thing as a Poisson-Lie T-duality group? What I mean by that is this. When you think of T-dualities as dualities between sigma models on, certain pairs of toroidally fibered targets of the two-dimensional sigma model, then you can also, by the duality defect correspondence, but probably originally due to Fröhlich, Runkel, Watts, and others, you can think of drawing defects in the world sheet of the two-dimensional sigma model, putting data of, well, T-duality, or your favorite duality, on it, and then you can intersect these defects. And then you have to pull something back to the junctions. And the junctions sort of set a certain, put a certain group, I put it in sort of inverted commas, a group structure on the set of dualities. I think it's an open question in the T-duality world, in the two-dimensional sigma model world, but do you see any binary operation on Poisson-Lie T-dualities?
I don't know about any such thing, but it sounds interesting. So I'm glad to talk afterwards. But so here, okay, I don't know if this is very much related to what you said, but well, obviously here you can take different, like more of those Lagrangian subalgebras. They don't have to be. Doesn't have to be two of them. You can have many of them. You can have even continuous families sometimes. And all of those models will be dual to each other. But as for multiplication, yeah, I don't see it at the moment. Maybe
So just at the not to continue the
Okay.
This goes in the direction of Kristall's T-folds.
Okay, I see.
T-duality to form manifolds that are locally modeled on toroidal fibrations, and the gluing data, some like transition maps between those local models would not be diffeomorphisms, but these would be data of T-duality between the corresponding
Right.
sigma models.
Okay, thank you. Yeah, so yeah, I don't know about such thing in this context, but I'm happy to discuss it. Okay, so, oh yeah, maybe to explain the name Poisson-Lie T-duality. So the name comes from the following thing. So suppose that you have the same thing as here, but furthermore, you want those two guys to be transversed to each other. So if you have H prime, so basically as a vector space, you want G to be sum of these two Lagrangian subalgebras. And in such a case, if you take the corresponding groups, H and H prime, then they are what is called dual Poisson-Lie groups. Sorry, H prime, H double prime. So these are called Poisson-Lie groups, and there is lots of classes of those examples, and which provide then examples of the Poisson-Lie T-duality. So this is the original example, which explains the name. But since then, there is many ways how you can relax that. So first of all, you don't have to assume that they are transfers. And but even more, you can just consider more general starting point where this thing in the middle doesn't have to be over a point, and this is what is called Poisson-Lie T-duality with spectators. And even more, and that's what I want to talk today. That's if you can get even more examples if you consider reductions. So maybe just before going into reductions, I want to say a few words about the relation to supergravity. so far we discussed the relation with the sigma models. So supergravity. Okay, so strictly speaking, I will be talking about only the bosonic part of it, and for the start, only about without Raman fields and gauge fields. So basically, this is just bosonic, the low energy effective action for the bosonic string. But yeah, at the end, I want to say something about type 2 and type 1 in heterotic. Yes, so here, let me be slightly vague, and let me just say that there exist, so there are two natural tensors that one can associate it to the data of a Courant algebroid, a generalized metric, and a divergence operator. So, and those two tensors are, one of them we call it the generalized Ricci tensor. So it depends on V plus and on divergence. And this is a vector bundle map, or yes, okay, so this is a, or okay, we can say, using the inner product, that this is a section of V plus tensor V minus. So it has two indices. Okay, so this is one of the tensors, and the other one is generalized curvature, generalized scalar curvature tensor, which is a function on the base. And let me not write down so the point is that we can define those for arbitrary Courant algebroid. Now, I will not write explicitly what they are. You can find them in the article. It's not that illuminating. The important property that those tensors have is this one. So there is a, okay, let's call it theorem. That theorem says that this generalized Ricci tensor and the generalized curvature are compatible with pullbacks. Compatible. So what does that mean? It means that I have such a pullback situation. Then I have a Courant algebroid E over M, and I have this one. And if I put a generalized metric and the divergence here, and construct the generalized Ricci tensor, let's say, and then I pull it back, I get the same tensor that I would get if I would pull back the generalized metric and divergence and construct the tensor there. So these tensors are kind of natural with respect to Courant algebroid pullbacks. But this by itself means, so corollary or consequence. So first consequence is that Poisson-Lie T-duality is compatible. Yes, sorry, I forgot to say one thing. Okay. Yeah. So before that, if in the special case when E is exact and the divergence operator comes from some volume form, comes from some mu in the sense of the remark before here. So if you have a volume form or a density. So if we have such a situation, an exact Courant algebroid and divergence coming from a density, then the claim is that the vanishing of the corresponding Ricci tensor and vanishing of the corresponding scalar curvature, this corresponds to string background equations. So this is or these are okay, let's call it string background equations. Meaning that if you take the low energy effective action, or like the supergravity, if we would have other fields, then these are the equations of motion of that supergravity. Yeah, okay, so and now I can go to corollaries. So the corollary of this fact that it's compatible with pullbacks, and the fact that Poisson-Lie T-duality is basically just pullbacks. The corollary is that Poisson-Lie T-duality is compatible with these string background equations. Okay, let's string background equations. So that's one corollary. So this is just a direct consequence of the fact that this is compatible with pullbacks. So if I have, for example, here, if I have two models, I construct the Ricci tensor corresponding to the generalized metric here, then since this generalized metric was pulled back, then also the Ricci tensor here will be pulled back from here. So in particular, if it's 0 here, it's 0 here, and therefore it's 0 here. So if we have a solution which satisfies these string background equations, then if you have any other which is Poisson-Lie T-dual to it, then that one will again satisfy these equations. And at the same time, so this is one corollary. And second corollary is that this gives you a powerful way to calculate or to find solutions of these equations by basically looking at this part of the diagram. So you just have a Lie algebra over a point, and these tensors, which I didn't write to you how they look explicitly, but these tensors will become just some algebraic objects. And you will have just some algebraic equation, and if you find, so if you find on a Lie algebra, so we have, let's say, quadratic Lie algebra with pairing, if we find on this guy some V plus and divergence, such that generalized Ricci and the scalar curvature are 0, then for any Lagrangian H, we get a solution to these string background equations on G mod H. So each time so it's enough to search for solutions here, and then we produce solutions here. Okay, so far, what I've said was more or less what Pavol was saying. No, it's okay. I will try to do both.
So it's a very quick question and very late maybe, but so the divergence operator that you defined, I can think of it as a codifferential of this operator rho transpose D, or?
A codifferential?
Like the analog of interior derivative for this rho transpose D? Or? In other words, if you wanted to form the Laplacian, would you take div rho transpose D plus the opposite, or?
No. The formula for the Laplacian is different. It has it is even quadratic in the divergences, I think, or something like that. So I don't think it's. Thank you. Yeah, I never thought about it that way. I don't know if you can see that, like that. Yeah, I don't know.
Okay.
Sorry. Yeah, but that's an interesting and natural question. So one should think about it. Yeah, thank you very much.
Sorry, one more question. So can you give us some intuition of the generalized metric on a Lie algebra? That's what you're considering here, right? Mm-hmm. So what's the G and what's the H in normal language?
You mean the metric and the...
Yeah, so you say a generalized metric corresponds to a choice of metric G and 3-form H. So what is it?
Yes, that's a good question. So this correspondence is only valid on exact Courant algebroids. So it's not. So that's the beautiful thing about it, that you are. But
aren't you assuming here that they are exact for this Poisson-Lie T-duality?
Yes. So you need that these guys are exact. So these are the places where you have a connection to physics. So it's only on the exact Courant algebroid that you get that these equations correspond to the usual equations that you have in string theory. But to see that you have some sort of duality, you have to go through something in the middle which is not exact. This would be, in the special case, this would be the Lie algebra over a point. So so or maybe said otherwise, it's only on exact Courant algebroids where you get this correspondence between metric 3 form and generalized metric. On a more general Courant algebroid, such as a Lie algebra over a point, which is not exact, here it doesn't. You don't have such an interpretation. There is just some subspace.
Okay. So suppose I consider an exact case. Sorry, so on a Lie algebra, if it's a pure Lie algebra, it's not exact.
Yes.
But on a coset space G mod H, it is.
Yes.
And so what is it on G mod H?
You mean explicitly? Also,
yeah, is there something you can say? Like, what is the G and what is the H? Or what are the possible...
Okay, so, well, explicitly it's those expressions that people write in Poisson-Lie T-duality, that you have this ugly tensor with... yeah, but
that's why I'm asking, because I never see those expressions. That's anyway. Okay, we can discuss later. Thanks.
Yes. Okay, thank you. Okay, very good. So let me talk about reductions. So reduction is a process that you can do with a Courant algebroid. So you can do pullbacks and you can do reductions. So pullbacks correspond to Poisson-Lie T-duality, and if you use pullbacks and reductions, then this will correspond to this equivariant Poisson-Lie T-duality. Okay, so suppose that you have a Lie algebra, which is unrelated to the Lie algebras before, so let's call it maybe S. Let's S be a Lie algebra. That's maybe not the best name for a Lie algebra, but that's what we use in the article. Okay, so now you say that, that's the definition. So a Courant algebroid E over M is called S equivariant. If there is a map, let me maybe call it, let's say chi, that goes from Lie algebra to sections of E. Yes, thank you. Such that it preserves the bracket. So if you take two elements of G, if you take X and Y, sorry, in S, so you have two elements in S, then you want to have that if you map them and take the Courant bracket of or take the bracket, then this is the same as if you would take the image of the commutator. So this is the commutator in S, and this is in E, so maybe, okay. And the second thing you want to have is that those guys, their inner product is 0. So in general, okay, here I'm having some special case of the definition. In general, you allow here to be some pairing, which can be degenerate, and then you would ask here that this is the same as a pairing of X and Y. But the only case which I will consider is this one where the pairing here is 0, so this is enough definition. This is okay for us. Okay, so this and this, and let's say the technical condition and chi is injective at any point. Yeah, in any fiber. Because I want to because for the thing I want to do with it, I want to take some. I want to take the subbundle which is spanned by these sections, and then I want to do some reduction with it. And I want that it at least keeps the rank, and yeah, and I also want that. Okay, it will be clear hopefully in a moment. Yeah. So this is not. Yes, I guess. Mm-hmm. So this condition, it will be visible, I think, if in the next step that I want to do, I want to suppose that, so because each time you have such a thing, then since you can use the anchor to map sections to vector fields, then you will have an induced action of the Lie algebra on the manifold. And I want this to be a free and transitive action. So for that you need that this is injective, I think. Okay, and one last definition. So if so there is a, so as I said, so if you have an if you have an S-equivalent Courant algebroid, then this means in particular that there is an action of S on the base, and also in fact you can since the sections can be seen as somehow inner derivative of the Courant algebroid, there is an action of S of the Lie algebra on the whole in the usual sense. There is an action on the vector bundle. And okay, so I will just, this is what I want to say. So if the action of S on E and M integrates to an action of a connected Lie group, integrates to an action of group, which I will call S. So this is big S and this is small s. Then we say that this is S equivariant. Then E is big S equivariant. Okay, and now the important thing that one can do with this, one can each time we have such a thing, we can do a reduction. So suppose the action of S on M, the one induced by such a structure, is free and proper. And let us call S with a subscript E. So this is a subbundle of E spanned by these sections chi x in S. Okay, so G is, so S is a Lie algebra, finite dimensional, so we get finitely many sections, and those sections, if this is injective at every point, they will create some subbundle. And so now we can define what is called a reduction of the Courant algebroid by S. And this is defined as follows. So first of all, we take this SE. This is a subbundle. We take its orthocomplement. So this SE, because of this condition, SE is isotropic, because the induced pairing is 0. So therefore, if I take the orthocomplement, it will contain SE. So I can make then the quotient of this subbundle by this subbundle. And this thing is still a vector. This is some vector bundle over M. And now what I want to do now, and on this vector bundle over M, there is an action of S. So now I will take the quotient of this guy by S. And the claim is that this vector bundle that I get over this quotiented space has a natural Courant algebroid structure which descends from the one on E. So this is a Courant algebroid. Yeah, a cool thing about it is that there is a much more conceptual way to work with Courant algebroids using graded symplectic geometry. And in that language, this thing is just a coisotropic, this is just a Hamiltonian reduction. So if you like Hamiltonian reductions, which you probably do, then this is the right way to phrase this. But I'm not going into this because then one would need to introduce some language. Very good. And now the claim is that, okay, no, easy to check claim is that if the original one was exact, then also the reduced one will be, then is also exact. Very good. Okay, very good. So now we know how to reduce Courant algebroids, but our Courant algebroids are equipped with some structure and with some generalized metric. So now we want to know if we can reduce a generalized metric. Well, so obviously not every generalized metric can be reduced because you know, it has to at least lie in here. So there is a notion of an admissible generalized metric. But to do that, I will slightly cheat and I will modify this definition at the beginning of a generalized metric. So a generalized metric, so this is the one that people usually consider. But in fact, for the formulas, or almost all the formulas, you can forget about this property and only want that this thing is non-degenerate. Yeah, some things will no longer be true, like, for example, this one, whatever. But the idea, all the formulas, the Ricci tensor, scalar curvature, everything stays the same. And it's useful to consider such a general notion because then we can, it's non-degenerate, because then we can define that, we can say that a generalized metric is admissible if, so V plus, if it lies in this SE perp. Yes, that one we need because we want it to, you know, descend, and we're only taking here the ortho complement of that. And second thing, since we are taking invariant sections, then we want that and V plus is S invariant. So this is just some natural conditions for it. And you can do a similar thing for the divergence. You can see what are the conditions for the divergence to descend. And I am writing all of this because there is a yes, okay. Let me maybe finish with that. So there are two things that you can do with this construction. I will just use this one. Okay, let's see this one. Okay, so far it's not clear how this is related to some dualities, and to see that, let's look at an example. So just as before, here, if we wanted to obtain a duality, we considered some G and some Lagrangian subalgebras. So one can start doing the same here. So we have some Lie algebra with an invariant pairing, and we have some Lagrangian subalgebra. If we want to have a duality, we can have two of them. But okay, so let's suppose we have one of them, and let's suppose furthermore that there is. So this is Lagrangian. And here, suppose that this is isotropic, right? Because of this condition. And okay, so now if we have such a thing, and okay, let's suppose also that H is transverse to S. Okay, just technicality. So as before, we have this Lie algebra over a point, and we have this map from G mod H. G mod H, and as before, this is exact. Right, so that's just a picture from there. And now, if there is, so if this is a subalgebra, then you can see actually, if you now take the, let me write it like this, the embedding, so this is our chi. Yeah, so this is, so in fact, this is, G is S equivariant, because it satisfies those properties. So let me call it like this. So there is an action of S on this one. And since this guy is basically pulled back that guy, then there is also an S here. And now, if everything goes well and something is free and proper, whatever, then you can do reduction here. Because this is a Courant algebroid, which is S equivariant. So if we do reduction, then what we obtain, so at the bottom, so we have some manifold G mod H over S. So we do a quotient and then a further one. And we get some algebroid over it. So let me just write, we get an exact Courant algebroid over this guy. It is exact because of this property. Because if we do reduction of exact, it's still exact. And now we can do the same game as before. We pick any generalized metric here, satisfying this admissibility property. This is not too strict. Admissible. This thing will give us generalized metric here. And then this will reduce to here. So we have some generalized metric, let's say like this here. And as before, generalized metric, exact Courant algebroids, this is the same as having some metric, okay, and a 3 form. Yeah, this is different G and H. This is a metric and a 3 form. And again, you can build a sigma model out of this data with the same action function as before. And the claim now is that if you take the same setup, but you only change this H, you take a different H, and then you do the same pullback and reduce, then what you get at the end will be dual to this one. And this is called Equivariant Poisson-Lie T-duality. And probably some people might know this construction under the name dressing cosets. So it's an equivalent name. Okay, let me just say maybe one last sentence. And the last sentence is that this story was concerning sigma models, but again, you can prove a theorem here saying that these guys are compatible not just with pullbacks, but also with reductions, which implies that the equivariant Poisson-Lie T-duality is compatible with string background equations. And at the same time, it allows you to search for solutions, just studying this algebraic setup, solving algebraic equations. And yeah, that's it. And a thing which I did not manage to say, but if anyone is interested, I can show how one can encode the Ramon-Ramon fields so that you can describe type 2 supergravity and how you can do heterotic string theory. So there's a natural way to define structures apart from V plus and divergence, which would encode both Ramon-Ramon, so either Ramon-Ramon fields or a connection. Yeah, but so thank you very much, and sorry for being slightly over time.
Thank you. I'm interested in type 2.
Okay. Oh, is that what I should do now, or? So that was a question, right? Okay. So I can be. The idea is simple. The idea is just that. So the whole of this Poisson-Lie T-duality business, it's about formulating stuff on general Courant algebroids, because Poisson-Lie T-duality is something that it tells you a relation between two exact Courant algebroids, but going through something which is not exact. So now there is a question: how do you formulate what is a Ramon-Ramon field on an arbitrary Courant algebroid? And so the answer for that is quite simple, because on T plus T star M, you can consider, okay, if you have general Courant algebroid, you can consider spinors. So you have some spinor bundle. So spinors. Since there is a pairing here, so you can form a Clifford bundle, and then you can form spinors. And yeah, and or even better, you can tensor this with a bundle of half densities. So you can have spinor half densities. Half densities, they are better in some sense. So, and for example, if this E is now exact, then the spinor half densities that you get is just the bundle of differential forms. So spinor half densities are just differential forms on M. That's a cool fact. And and Ramon-Ramon fields are objects which live here. So they are spinor half densities. And now there is a cool thing on Courant algebroids, that every Courant algebroid admits something which is called Dirac generating operator. So Dirac Dirac generating operator. It's some canonical operator which acts on spinor half densities. And if you look at what this Dirac generating operator is for these guys, then this will become just D plus H. So that's the property that you want for Ramon-Ramon fields. You want them to be closed under this differential. Then what else do you need? You need that these forms are either purely even or odd. So for that, there is a notion of parity. So that if you form an arbitrary spinor thingy, then you still have a Z2 grading here. So if you take either even or either odd spinors, then this will correspond to type 2A and 2B. And a self-duality condition is also something that you have. So if you have a generalized metric here, then this is if you take reflection with respect to it, the reflection with respect to the V plus is an element of pin, of the pin group. Or actually, sorry, no, it's an element well, anyway, it's an orthogonal, it's a map of ON. So if you lift it to pin, then it acts on spinors. So what I'm saying that there is a natural reflection operator associated to this generalized metric. And you can then require so that this reflection operator, it preserves these forms. And the advantage of these guys is that they make sense on an arbitrary Courant algebroid again. So you can study them over a Lie algebra again, where they are just some spinors. And then if they, then the string background equations will look somehow different. So there is a right-hand side here containing these things. But so you can encode them, and it's quite natural. It's a different. They enter on a different footing. They are not part of the generalized metric, unfortunately. But you can still work with them, and you can. So in fact, what we did with Pavol, we found some new solutions. Let's say for generalized supergravity equations by just looking at this setup with reductions with S and with some stuff here. Thank you for the question.
Other questions that sound more like questions?
So you said at some point this generalized metric, you can relax this condition that it's just non-degenerate. What effect has it on this relation to metric and three-form field? And
yeah, that's a good question. So yeah, so that's the point where it fails. Yes, so that statement as I wrote it is not true that there is a one-to-one correspondence, because for that you need really that. In this picture which I erased, you wanted that this could be seen as a graph, so we should have the same rank as T. But in this construction of the Poisson-Lie T-duality here, see here, so the idea is kind of, so here you have to pick a smaller, so that's why I needed to relax this condition, because here I want to now pick, for the purpose of building some theory, if you want to pick this admissible one, you want this to be smaller, not half-dimensional, but smaller, such that if you pull it back here, it's still smaller than, it has less than half rank, but after you quotient it, then you get something which is, so in this quotient process, you are killing part of the rank becomes smaller. So if you choose a particular one of, a particular V plus of a good dimension here, then here it will not correspond to a metric and a three form, but in the quotient it will. So,
thank you.
Yeah, that's a good question, thank you.
Exact Courant algebroids are classified by this Ševera three-form cohomology class. Is it clear that in the first part that there's a representative which is S invariant on the top on E, or otherwise what would be the free-form class on the reduced Courant algebroid?
Yeah, that's a good question. Yeah, so sorry, at the moment I don't remember how this. Yeah, I remember we never needed to worry about this tree form being S-invariant, but I would have to think a little. Yeah, I cannot tell you from the top of my head, sorry.
And in the restricted case where you have this...
Maybe, but... Yes, then you do, but... or maybe it comes for free from such construction. I don't remember. Yeah,
Probably, that's what I would imagine. Do you maybe know in the special case where you have this generalized metric, then I suppose that the metric, I think that you get a degenerate metric, right, up there, which is probably strictly S-invariant. And maybe
Probably.
H is also S-invariant, and it just descends in a very natural way. Is it like this?
Yes, it seems so. Yes, I think so.
Okay. Thank you.